Hi all, I am D. Senthil Kumar, Assistant Professor in the Department of Mechanical Engineering of Vellala College of Engineering Technology, Erode. I am now going to deliver a course module on thermal stress. First of all, what is a stress? The stress means the resistance to the external force developed by a body from within itself per unit area of cross section of the body. Its unit is Newton per meter square or Pascal. There are basically three types of stress. When a tensile force acting on the component, then it is known as tensile stress. Other two types are compressive stress and shear stress. Then what is strain? Under the action of external force, there will be some changes in the dimensions of the component. The change in the dimension to the original dimension is known as strain. When the component elongates, then it is known as tensile strain. When the component shortens, then it will be known as compressive strain. And if there is a change in the volume of the component, then such a strain will be known as volumetric strain. So we are into the main topic now. Let us start with an application part. We could have seen railway tracks with some gap between the rails. What could be the reason for the gap? During hard times, there will be some expansion in the material of the railway track. So if there is some gap in between the rails, the rails will be free to expand, so that there will not be any stress developed in the track. If the expansion is restricted, there will be some stress developed in the material, so that when a train runs on the track, due to the heavy load and vibration of the train, there will be stresses developed in the rails and it may lead to failure. This is the reason why we are keeping some gap between the rails of the railway track. So let us now understand the concept of thermal stress. Thermal stresses are the stresses which are induced in a body due to change in the temperature. If the temperature of a body is raised, the body will tend to elongate, and if it is lowered, the body will tend to contract. If it is allowed to expand or contract freely, there will be no issue. But if there is a prevention of expansion or contraction of the body, then it may lead to thermal stress and thermal strain. Let us consider a body AB, which is fixed at one end. If there is no support at other end, and if the body is heated to a temperature T, the body will be expanded to a minor length dl. So here L is the original length of the body, T is the rising temperature, E is the Young's modulus, alpha is the coefficient of linear expansion of the body, which is a material property, and dl is the expansion of the body due to rising temperature. So if the body is allowed to expand freely, there will not be any stress or strain developed. But if we keep a support on the right side also, the support will exert a compressive force on the body, which will prevent the body from expansion. So here, the prevented expansion of the body is L into alpha into T. So the thermal strain developed in the body is nothing but dl by L, which is nothing but alpha into T. According to Hooke's law, stress is equal to strain into Young's modulus. So the strain is del L by L, that is alpha into T, and hence the thermal stress developed is E into thermal strain, which is alpha E T. The second case is that the supports do not prevent the expansion of the body completely. The support will yield to some extent. Here, if the support yields by an amount delta, then the prevented expansion will be L alpha T minus delta, and hence the thermal stress is L alpha delta T minus delta by L into E. So these are the two cases in case of simple bars subjected to thermal loads. Now, when considering thermal stress in composite bar, let us consider a brass rod and a steel rod, which are rigidly fastened together. When the brass and steel are separated, due to the difference in the coefficient of linear expansion of the brass and the steel, since brass is having higher linear coefficient of expansion than steel, the free expansion of brass under thermal load will be higher than that of steel. But as a composite rod, these two have to function as a single unit, and hence the final change in the length or final elongation of the composite unit will be slightly lesser than that of the free expansion of the brass, while it is slightly higher than that of the free expansion of steel. How is it possible? The steel will exert a compressive force on brass, and the brass will exert a tensile force on steel, such that the elongation of brass and steel are same. Here, due to equilibrium, the compressive load exerted by steel on brass will be equal to the tensile load exerted by the brass on steel. Also, we know that the final expansion of steel will be equal to final expansion of the brass, because these two form a composite bar, which is a single unit. But actual expansion of steel will be equal to the free expansion of the steel under thermal load plus expansion due to the tensile stress exerted by brass on steel. So alpha S LSTS plus sigma S by ES into LS. And the actual expansion of brass will be free expansion of brass minus contraction due to compressive stress induced by steel in brass. So alpha B TB LB minus sigma B by EB into LB. As the final length should be equal, alpha S TS LS plus sigma S by ES into LS will be equal to alpha B TB LB minus sigma B by EB into LB. If the lengths of steel and brass are same, the final equation will be alpha S T plus sigma S by ES is equal to alpha B T minus sigma B by EB. So this is the concept behind thermal stress acting in railway tracks. So in this lecture, we have learned about the thermal stress in simple bars and compound bars. Thank you.